Good afternoon, everyone. My name is Rafi. I'm going to talk about debugging a live Gluster file system using a special directory called meta. So before jumping into the agenda, I'll introduce myself. I'm Rafi, as a software engineer at Red Hat. I've been at Red Hat for 3 years, almost 3.5 years. I've worked in components like RDMA, which is remote direct memory access, and snapshot, and then tiering, and then replication. That's pretty much about me. Let's see what we have for today. So we'll have a quick overview of Gluster, and then the architecture of Gluster as in like an overview, because it involves like a demo. Most of the talks involves a demo. So I'll explain the architecture a little bit, and then I'll introduce about the meta translator, and then the basic commands it provides, and then more advanced options through the meta, like frames information, memory information, and the graph information, and the translator like master translator. And then finally we'll end up our session with the future enhancement, and then question answer session. Yeah. So as everyone knows, Gluster is a distributed file system. It's a software defined network attached storage. It has multiple nodes which participates in a cluster to provide one single namespace that can be accessed via Gluster native clients or NFS clients or SMB, or we have written around libraries called libgf API. You can access Gluster volume using either of these access methods, and yeah, it works either through TCP/IP protocol or RDMA protocol. Yeah, so Gluster has a very modular architecture. So how it is achieved is using something called as a translator. A translator is a module which gets an input, and it operates on that input, and it passes that information and the input into the next translator. So all of the Gluster process or binaries are working based on a graph, something called as a graph. A graph is nothing but a collection of translators. So I have a picture here. It's a picture for Gluster mount process and a server process as well. So what it does is, for let's say a file system operation, when a file system operation starts, for example a read operation, it starts from the kernel VFS layer, and then it will be given to the user space fuse process, which is this process here, and then we have something called as translator, which is this one. So this is the graph we have. So the graph is a representation of multiple translator. So this process works based on this graph. So let's say a read operation comes on from the VFS, it will be given to the first translator on the graph, and then it does its operation. For example, in the first here the first translator is the IO cache, which is nothing but like the page caching. So let's say a read operation comes. So on an offset, so the IO cache translator checks whether there is any page hit on already cached contents. So if it has a page hit, then it serves from here itself, and then will be given the data into the back to the VFS. Otherwise, what it does is it creates a page fault, and then it will given the read call into the next translator, and it flows from here to here. And this is a distribute translator which does the distribution for the Gluster, and we have a replica translator which does the replica. Let's say we have a forward distribution, which means you will have a for child for the distribute translator. Let's say we have a 3-way replication, which means you will have a 3 child for the replica translator. That's how it works, and then the client process will be given to the server, and on the return path, let's say you read the content from this disk, then it will flow from here to till all the way to the VFS, and then let's say for this IO cache, it creates that it stores that newly created page, and it works on the next read call. It serves from this one. This is the basic architecture for the Gluster, and this is the translator model. So I explain this because when we debug the Gluster, we have to look into the different translators, what options they have providing, and how we can look into the options, the file system specific frames and latencies, all those things. That's the reason why I explained this big architecture level informations. Okay, so now talking about the meta translator, which is the main talk for this. So it provides a dynamic information about a mount process. Let's say we have a fuse mount process that accessing a Gluster volume. What it does is it provides a dynamic information like the memory information, what are the file system operation is ongoing, and what are the internal operation that resulted, let's say a read operation, or let's say a rename operation which involves a lock internally. So what are the operation is ongoing through the Gluster mount process. All those kind of dynamic information you can fetch through the this special directory. So it's very similar to Linux procfs. You might already know about Linux procfs. It gives the kernel level memory informations and process wise, like the OpenFDs, all this information for a kernel for a Linux operating system. So it's very similar to the procfs file system. What meta does is in the Gluster root there is a hidden directory called .meta. It's not only hidden but it's also virtual, which means you cannot see that directory. Even if you do ls or ls minus r, you can't see this meta directory because we don't want to return any of the read repeat calls. This .meta should not be returned to the application layer, because if at all you are doing a CP or r minus rf, that .meta directory should not be exposed into the top layer. So that's why it's a hidden plus virtual. You cannot see. If you are just doing cd to .meta, you can go to the into that directory, but you won't see that directory in any of this listing. So that's and yeah. So as I said, it's a translator. So writing a new feature in Gluster is very simple. You need to write a translator and put it into the appropriate position in the graph. So this translator, but this is a special translator. It is not actually present in the graph, but it's automatically loaded into every mount process. Every mount process in the Gluster, it is automatically added. So you cannot see in the graph, but it is automatically added. And this is useful for debugging purpose and as well as the monitoring, because what you can do is you can see the latency for each of the file system calls. You can see those how much is the latency for each translator through the meta translator, and the DU information, disk usage for each servers. You can see those information using this translator. So the good thing about it is that you don't need to do anything. You don't need to alter. You don't need to send any signals to the process. You can just access through a directory, file directory structure. So like you don't need to put a NES system tab or GDB to get all those information. It gives high level information like what are the frames, frame information for each calls. So I'll start with the basic commands for the meta translator. So I'll switch into, so I'll give you the, I have a volume here. This is a very simple volume. It's the volume name is called Apache. It's a distributed replicator volume, and it's a two-way replicator and a two-way distributor. That's 2x2. These are the servers. The volume is started. You can see here. So the volume is started, all the volumes are running. So what I am going to do is I'm going to mount this process. So I'm going to mount this as mount minus t glusterfs. I'll just quickly do this. So I'm going to mount this into /mnt. I'm going to mount a Gluster volume called Apache into /mnt. These are the mount options. The event history on is means the eventing for the file system operation eventing is turned on for this mount process. Okay. So I'm sorry, it's already mounted. I'll first unmount. So it's already mounted. Sorry. So this is the mount point. There is nothing in here. So so now if you do LL, you can't see this .meta directory. LS, yeah. Sure. Sure. I'll also increase the. Does this work? Okay. Okay. So if you do ls, you can't see that. Even ls minus lrta, you can't see that .meta directory because it's a virtual directory. So but if you do cd to .meta, it is now moved into the .meta. If you do pwd, you can see it's currently in the /mnt in .meta. Now we can see what are the information .meta provides. So I'll start with the simple things. So if you do ls, if you do ls, you can, okay, I'll do one thing, I'll make it ll. So you can do this command line arguments, memory information, process latency, UUID of the process, versions. So I'll start with version. So version is very simple. It provides the Gluster version as a JSON format. It's actually there. I mean, it is there. It's actually. So the package version is 3.10.10. So and then you can see the command line arguments. So you can see the command line arguments which this mount process is started. Which the process is user local has been glusterfs, and the argument is the history is on, and the world file server, which means the server host name, and then the volume ID, which is the volume name, and then the mount point. This is the process. This is the process which is started, and then the other information about the logging. So in most cases we wonder where is the logging file is. So if sometimes you can configure it through the command line when the process starts, or you can configure it with volume options. But if you don't know, you don't need to search for this volume file. What you can do is you can just go to the .meta directory, and there will be a logging directory here. So you can just go to here, and then you can see the okay, so here you can see a log file, which is nothing but a symlink to the actual log file. So if you want to see the log file, you can just go to the meta directory, and you can do ls or whatever it is to the log file. So now you can see the log file. So if you don't know about the log, where exactly the log file is stored, but you can just go to the meta directory and see the log files. And another important thing about the log is, let's say you have multiple client process for a Gluster volume. Let's say thousands of client process are there for a single volume, which means you can have a log level for your log file, like debug log, trace log, and critical logs. But you can also change it, configure it, like through a Gluster commands you can change that log level into trace or debug or warning. But that changes the log level for all the clients. Let's say you want to debug a particular client process. You cannot just you cannot just change the log level for a single process. Of course, you can restart the process with the log level as a debug or trace, but it requires a restart. So how do you change log level of a single client process? That you can do using this log level. So there is a file called the log level. So you can see what it has. So okay, sorry. So it's locking the system. Okay, so actually it is there. I don't know how to adjust it. So the log level is actually 7 right now. You can change the log level, like the log level, there is a log level number. For trace it's 8, for info it is 7, so something like that. So to change the log level, what you need to do is you have to rate the log level number into the log into this file, log level file. So let's say currently it has the log level of 7, which is written there, but it's not displaying it. But I'll just do a demo, like changing that log level into a 8, which is trace. There is a documentation what are the numbers for each log level. So what you can do is you can change the log level through this interface. So now the data is written, and you can see the log level as 8 here. And now what are the changes it has is, Now if you select log file below, you can see it is started printing the debug logs. Okay, so that's one information. Okay, I'll quickly move. So that's about the logging. Other things, yeah, the process UUID. So the process UUID is each client process has a unique identifier. So that information can be fetched through this process UID. Process UID. This is the process UID for this client process. How this is helpful is, let's say you have thousands of clients, which means the information about a particular event on the client in the server logs is logged through using the process UID. Let's say if you take okay, I'll just copy this one, and if you take the server logs is stored here in the as a brick. See, if you search that thing, you can see the logging, like the logging for this client, like it says accepted client from this mount point. So let's say you have thousands of clients. There will be thousands of lanes like this, that the connection is establishment has already happened, or the disconnect has happened, with the process UID. So if you want to know whether the connection happens or disconnection happens, you just need to take the process UID and search that process UID in the server graph. And also when client makes a locking into the servers, if you want to know which especially when you debug a deadlock kind of scenarios or a locking issue, you want to see which client has taken a lock from the servers. So in that case, the locking has done with this process UID. So you take the process UID and search in the locking translator which client has taken the lock. So you can use the process UID for that, for those kind of informations. The other thing is memory information. Yeah, that's very important. So you can see the memory information through this meta interface. So okay, I'll go to the front. I'll open through this one. See. Yeah, so for a Gluster process, for a Gluster client process, you can see what are the memories this Gluster mount points as using this meta interface, and that's through the mat info file. So it says what are the arenas, it's already allocated, the blocks, the mapped informations, and yeah, the free blocks, things like that, and also from these allocated spaces for the memory for this process, you can also see what are the data structures, the particular data structures, how much memory it has already used. Like this is a data type, data structure which is used in Gluster, and how much says it has already consumed. Let's say you have a memory leak problem in Glusterfs and you are debugging it, then you can look into this you can look into this information and see what is the maximum size what is the maximum size allocated for each data types. And you can see when there is a memory leak, you could see one data type or one or two data type is using a lot of spaces, and that's why you can understand which data type is using this information. This is a global data structure, and there is also a translator specific data structure that you can see when we look into the graphs. Okay, and yeah, so now I'll introduce about I'll talk about the master translator then, because we don't have much time left. So this is the translator for the fuse bridge. So all the information about latency. So to see the latency information, what we can do is we can start some operation on the mount point. Then I'll go into a different terminal and go to here and dot meta directory and then master translator. So if you can see, we are here in the mount point dot meta translator and the master translator. and here what we have is a history. What history is, what are the operation as going, what is the operation is happening on the mount point. If you see the history, you can see what is the operation is going on on a fuse mount. So it says, for example, it has a time and what are the operation is going on. So this is like on an inode sending an invalidation operation, and this is an open on this directory because we did a open into that. We did a open in the history. That's the last operation lobe, and you can see the other fstat on the Linux. So all those operations, the fuse operation, you can see the history through this interface. That's one. And yeah, so and as I already told you about the profiling information. So you can see how much information. Okay, I think the profiling has turned on. Sorry. So you can see measure latency things. So you can enable the measure latency thing by writing 1 into this one. So then now it will take some time to measure the latencies, but let's see if it is already here. If it already turned on, you can see what are the yeah, but it will take some time. So basically you can see if you turn on measure latency into, if you turn on that option, you can see each latency through this interface. Currently it was turned off, so it is showing 0. The other things is the options of each translator. So you can see the graph information through this interface, which is, there will be a directory called graphs. You can go into graphs and see you will have all the graph histories in the graphs. Let's say a graph means, as I said, it's a collection of translator. So when you disable a translator, it is like a new graph because you have removed one node from the graph. Let's say you disabled a caching translator, which means you have a new graph. So that information you can see from this. What are the graphs, the graph history and everything, and what is the active graph. So I can show you a demo for that, like cluster volume set, performance. There is a translator called a write behind. There is a translator called write behind, which does the write in the background. So I turned off that that performance translator, which means the graph has changed because this translator is now removed from the graph. So you can see the old graph information through the meta. So see, now there were only 2 entries earlier, just one, this Rafi. Now you have 2 because this is an active one, which is similar to the already existing active graph. Now you can see one more graph is the old graph. So if you go into the active graph, you can't see the write behind here, but if you go to the old graph, you can see that information. So if you see here, you can see write behind here, but you can't see that write behind in the latest active graph. So all those informations, like what are the current graph and the previous graph, all those information can be fetched through this interface. Yeah. Okay. So so I'm winding up the session with. So I explained about the memory information, like this is an explanation of the each lanes, what each lane means, says, and the number of allocation, and the memory informations, what is each lane means. So you can refer into this one, and I'll talk about the future, and then we'll just find out. Yeah, sure. So what we are planning as a future for this translator is we are planning to give a future like a free and a drop cache through this meta translator. Let's say Gluster has a lot of translator for caching. So each translator stores metadata information or caches metadata information. So you can see what are the caching memory, how much caching memory is used, and you can also do a drop cache, or you can also do a drop cache to drop all the caching from the Gluster mount process. That is we are planning as a future. We are and yeah. Okay, I'm done. Any questions?
Sorry, no time.
Okay.
If you have questions for Rafi, I'm sure he'll be around at the Gluster booth building.
Thank you.